All right, absolutely. Thank you for your patience, ladies and gentlemen. Um, yeah, so I'm Jacob Monroe, and I'm from the United States. I just received my PhD in July. I've come to ISPIC as a research analyst, and I'm going to be conducting energy systems modeling and optimization. And today I'm going to give you a talk about my expertise and how it can be applied for research here at ISPIC. So let me give you a little bit of an overview of what we're going to talk about today. I'm going to talk about my expertise with complex systems, complex adaptive systems, sociotechnical systems. We'll talk about agent-based modeling, which is a computational approach for the above two. I'm going to talk about some of the previous work where I've applied agent-based modeling and socio-technical frameworks. And then we'll also talk about some future directions right here at ISPIC that I'm going to be applying ABM to. Although it's not a completely exhaustive list, there's many different directions that ISPIC goes. And if you have a wise enough imagination, let me know your thoughts after today's presentation, and we'll talk business. So let's start out with complex systems and the idea of complexity in a system. Well, system components locally interact in multiple ways to self-organize into a higher order. It leads to the emergence of pattern and order by internal processes. And that emergence happens without central authority. It's not top down, it's from the bottom up. And this gives light to the statement of the action of the whole is greater than the sum of the parts. And again, we're just looking at aggregation in general and how emergent behavior happens through combined simplistic rules for relationships. So complex systems, the interactions can produce nonlinear dynamics, where small changes in system properties can generate quantitatively and qualitatively different system outcomes. And these systems focus on irreducible complexity arising from simplicity. Again, bottom-up perspective there. And let's progress here to complex adaptive systems, where systems change and reorganize their components to adapt themselves to problems posed by their surroundings. The system does not just evolve over time, its past is co-responsible for its present behavior. And what does that look like? Let me show you an example here where we have a group of birds, which the group of birds together can create patterns through their aggregate flight path. Right? They have simple rules how each one of them flies, but then looking at it as a system whole, we see the emergence of these beautiful patterns. And the pattern constantly evolves based on the collective movement of the birds, of the agents that are at the very bottom of this system. And eventually they may adapt into a level of stability or quasi-equilibrium, even into patterns where the whole looks a little bit similar to some of the individual parts that make up that system, okay? Now let's talk about energy systems as complex networks, okay? Now there's many different individual pieces of energy systems that are interconnected into a hierarchical system of systems where each piece follows its own set of simple rules to function. And there are subsystems present in energy systems that dynamically interact and adapt to satisfy energy demand. We're talking about social subsystems, natural resource systems, environmental systems, of course, infrastructure systems. And each subsystem has its own set of rules to interact with the others. Now, also the idea of evolution, where energy systems are evolving. Their infrastructure operations and dynamics can evolve and adapt because of environmental impacts, natural resource constraints, social acceptance and communication. Really, the human behavior should be highlighted there because word of mouth really influences the infrastructure, and we can prove that with some of this modeling. Also, technological advances. And then the emergence of what we can be really thrilled about and seeing, and what utility managers want to know is, the emergence of electricity prices or the profile of that electricity price, greenhouse gas emissions, spatial distribution of load, and also grid stability patterns. Okay, this is looking at it. So now moving forward with sociotechnical. These are systems that consider the complex arrangement of interactions between humans and technology. The approach is designed to examine feedbacks that exist between complex infrastructures and human behavior. We're really looking for the emergence of system-level order from dynamics between social and infrastructure networks. Now, sociotechnical systems, this approach is we're modeling social and infrastructure systems explicitly and mapping their connections. Very similar to this graph that we see here to the left. Now, as a social system perspective, we have a social network of end users and operators and utility managers, and they each exhibit behaviors. End users can adopt new energy technology like solar PV and wind. They can adapt their loading schedule. They might have objectives for minimizing electricity demand. They can respond to market signals. We have operators that can optimize generation asset dispatch. They have objectives for balancing the network frequency. And then the really top level, we have utility managers, which can pass rates to the end users. They can adopt their own line of new energy technology at the grid level. They may have objectives for minimizing environmental pollution based on policy frameworks. And they might also have objectives for maximizing system value from a business perspective. Okay, so there's many different schemas by which you can look at that behavior. Now we're going to talk about the computational approach to sociotechnical modeling in complex systems, which is agent-based modeling. Now, what is that? Well, it's a modeling approach that simulates the actions and interactions of multiple agents within a closed environment. The solution method is for problems that involve a high level of heterogeneity. And essentially what we're looking for is the emergence of complex system level dynamics from the interactions of simple coded behaviors. Again, the ability for us to go into a computer framework and really spell out what those simple behaviors might be and how they will interact. Now, why would you want to use agent-based modeling and when would you want to use it? Now, for why, it's because it's very well suited for studying feedbacks, which are fundamental to many ideas about complexity. The rules governing agent actions are bottom up instead of top down, and the complexity emerges from this simplicity. This is what you're trying to look for. And also, why ABMs explicitly integrate cognitive processes of agents through decision-making processes, and the ability to code out those decision-making processes, make it good for human dimension and how that may impact infrastructure systems or certain renewable energy programs or sustainable communities or resilience in communities. But really look at the human dimension is very important for this. Now, when would you want to do it? Practically, when there's a high degree of heterogeneity present in the system, you have a lot of different actors and agents, and they all have very different functionalities. Looking at a number of agents or objects that you might be modeling, a medium number of agents where it's greater than one, obviously, but maybe less than 1 million or less than 10 million, really to put some bounds on it. Now, the one point to really bring up is the idea of when there's a rich and explicit environment. The ABM modeling approach is explicitly a spatial approach. So if you have an environment, which again in civil and environmental engineering and many approaches in energy systems, space matters, environment matters, regions and states and political lines matter. So when we're looking at rich and explicit environments, that's when you want to use an ABM as well. And last, what I'm going to talk about here is that human behavior and adaptations are important drivers. That's when you'd want to use ABM. So, again, simulating behavior with agent-based modeling. So ABM is well suited for modeling human decisions and behaviors. Each agent is given a set of rules to define behavior. And then there's also the interactions between agents are modeled explicitly. Agent-agent models are explicitly modeled, but also agent-environment and environment-agent interactions are also modeled explicitly. Now, this gives us some unique ability in ABM where we can track the state of each agent over time based on the given set of attributes. Okay, so agents have attributes and they also have rules that are defined to characterize the state of the agent, which are based on the values of the attributes. And there can be many different states. And tracking that state over time gives us some pretty interesting ability because when we're modeling on the unit, we're able to look through simulation runs and see what happened to each individual object, which you don't actually have that freedom with using differential equations model. Everything sort of gets sucked up into the equation. Whereas with this, we're modeling each individual moving agent. And we're mapping the impact of human behavior from agent-agent interactions, agent-environmental interactions, and environment-agent interactions. Now, the application areas, this is what we're going to talk about now, and where I've actually applied these in the past. The first sort of bout that I had with ABM was applying it to critical infrastructure protection and simulating attacker defender games. And the approach that I had was, this is when I was working on water systems. And water distribution systems in particular. Well, there's this huge call for research in the middle of last decade about lone wolf attackers and maybe having a lone wolf attack maybe an electricity supply system or water supply system. So essentially I created an attacker defender agent-based model where you have an attacker that tries to maximize public health damage by sabotaging nodes in a water supply system with a chemical agent. Use your imagination on what it could be. And also, we modeled defenders, which want to minimize the damage by providing defense or hardening nodes in the system. And what would that look like in sort of a process flow diagram? The ABM diagram we have here simulates the attack and defense of a water distribution system, where you have a defender, which could be really the utility agent, where they have two main jobs. They send information on where the police should rove, where their roving strategy should be. And they also allocate certain security equipments to the water supply system. And essentially what they're doing is trying to provide defensive coverage for the water distribution system. Then you have the attacker that has to predict the best node to attack, and also the node that they believe will not essentially be defended by the police officers. And then you have this chemical attack, which we then model with a public health system model and an actual EPA net water distribution system framework, where we map the plume of contamination that goes into the environment, and then we read the chemical exposure to the consumers. And some of the design concepts that we're trying to show here are the emergence of the public health disaster and how many people are dying, and sort of the spatial distribution of those dyes, or not necessarily death, but contamination. The objectives for maximizing damage or minimizing damage on the defender side, interaction with the water distribution system between the attacker and the defender in the water distribution system, mobility of the attacker and the defenders through roving strategies, and also looking at prediction, stochasticity, and sensing, just to give you an idea of the main terms that we're trying to illustrate with these models. So another application area that's probably a little bit more down home to ISFIC would be solar PV adoption and the death spiral, which we modeled with an ABM. I've developed a residential solar PV adoption model where households make the decision to adopt PV based on utility values for economic payback, environmental sensitivity, social communication, and household income. And essentially, these households make the decision to adopt the PV. And then we track what happens in the utility system. Again, when households make the decision to adopt, the utility loses revenue, and there's also grid instability problems that can result from the adoption of PV over time, which can then result in a utility rate hike, which rate hikes incentivize more PV adoption. And the cycle continues. And we can really see this right here. Or again, you're looking at household agents, and they can wreak havoc on the power system, and those infrastructure components can deteriorate. So the manager has to essentially repair those problems, and you're also dealing with a manager agent that's losing revenue. Again, there's an arrow missing here where the household agent should be paying revenue to the manager agent. So you're losing that revenue, and you're also having these infrastructure components deteriorate. So you can pass a rate hike to the household agents, and then as the rate goes up, this incentivizes the adoption of solar PV. So over time, you're left with some of the rich people or higher social or household income being able to buy all the solar panels, but some of the poor socioeconomic status individuals in the population are just stuck with an ever increasing rate for electricity. Okay. Now, something I've done more recently is using ABM and applying it to peer-to-peer energy markets. And this is a system where prosumers are going to swap excess solar generation with consumers in a peer-to-peer electricity market, right? So prosumers bid their forecasted excess solar generation for an upcoming 30-minute period, and consumers will bid for that excess generation. And what we're looking for from an ABM perspective is, how does the system price of that free market emerge from the market, the socio-technical dynamics in the peer-to-peer market? Okay, and again, we looked at actual case study in Western Australia for this, and we applied it. And here's sort of the diagram that we developed for it, where we have a string of single-family residential households. There was 18 for the system that we looked at. They're all very different consumption and generation patterns, depending on sort of their geospatial placement in the environment. And everything is hooked to the electric distribution system here. And again, you have a utility agent where you have a free market system where people can agree to buy their excess. But again, if you don't have anybody to offer that excess generation, you still have to buy it from the utility agent. And this is sort of a diagram that shows all that. And we're looking at, very heterogeneous, high degree of heterogeneity. We're looking at the emergence of, system price. We're looking at the interaction in a bilateral exchange market. We're dealing with prediction of forecasted excess for an upcoming period, which is very tough to do. We're also dealing with sensing market signals as well. So you can imagine how the adaptations can happen when you're reacting to a certain system price. So now one little toy sort of application that I wanted to show here, it's an illustration really, but I've been able to model or simulate micro trading of rainwater, where prosumers, very similar to the electricity market, they trade excess rainwater with consumers in a peer-to-peer water market. Okay, so prosumers are bidding captured rainwater that's in their tanks, and consumers are bidding for that water for non-potable uses such as irrigation and gardening purposes. And what we're trying to look here and find out is the emergence of the energy demand patterns for water reclamation facilities and household pump systems from those market dynamics, right? And so I'm not going to show you a diagram here. It's very similar to the peer-to-peer energy trading system. But what we're doing here is showing you that ABMs can model multiple infrastructure systems, because infrastructure to infrastructure interactions can be quite important, especially when you're dealing with energy. Well, water and energy are tied to the hip. We know this, and it's at many different scales and many different activities that do it. But just to show you here that ABM can be used for infrastructure to infrastructure interactions. And with this particular project, we looked at the feedbacks between human behavior, water resource networks, and electric distribution infrastructure. Okay, now I'm going to talk about some new application in energy systems for agent-based modeling. These are really just some low-hanging fruits that I see for my own research. There are many different applications in ISPIC and many other directions. And of course, if you're thinking about these during this presentation, use your imagination and come up to me and approach me or send me an email and tell me how you might see that AVM or sociotechnical analysis might be pretty good for your own project, because we know that human dimension is quite important, especially we're trying to achieve new efficiencies with smart grids and new sustainable community programs and platforms. So we'll talk about the first one, which is decarbonization by electrification, where we're trying to shift transportation and heating toward technologies that consume electricity instead of fossil fuels. Now, Canada has a unique opportunity to do this because Canada has an extensive renewable portfolio for electricity generation. Mostly hydro, there's some wind, there's some tidal, there's also some solar resource that some people are making advantage of. But essentially what I want to do with my own research would be to develop agent-based adoption frameworks for electric heating and transportation technologies. And the reason is because there's a few questions that come up with this. How will the dynamics of power systems evolve in the transition to a decarbonized Canadian energy system as facilitated by the adoption of electric heating and transportation technologies? How will the adoption of electric heating and transportation technologies then further affect the demand for electric power? And then how will the evolution of that electric power demand influence the operations of generation facilities and the planning for new capacity, transmission, distribution, energy storage, and charging infrastructure investment, just to go through a little bit of an exhaustive list. Now, here's sort of a diagram that I put together, just an example of exactly what we can do with ABM. And what I'm going to do is take you through here, look at the subsystems of the ABM. Again, many agent-based models can be construed of a system of subsystems, and that's what I'm going to show you through here, right? So we're looking at the auto drivers of the electric vehicles, and this is a social networking model. There's word-of-mouth communication between these drivers, and either the positive stimuli or the negative stimuli can influence their decision to adopt those EVs, right? So that's one subsystem, again, word of mouth. Yeah, so the other one is, you'd have to have facility operations models to see what's happening on the generation side with this changing demand. You'd also have to have a hydrometeorological scenario generator to see how different levels of meteorology can impact sort of the infrastructure that we're using to charge these vehicles, but also sort of the environment, which is the commons by which we're doing carbon emissions and dam releases. And then the last submodel here is the mobility model, which is the movement of those electric vehicles through space and time. And again, that's what makes it quite interesting. And that's sort of an overlapment with the social networking model as well. Now we can do the same thing for heat pumps. It's not as interesting because, sadly, heat pumps don't move around once you actually adopt them, or they shouldn't. But we can do the same thing for the heat pumps in the same set of subsystems minus the mobility model. So another direction with thinking about decarbonization, and this is looking at more of the utility side and what they're looking at, is the adoption of electricity rate structures where utilities are offering optional rate designs which encourage the shift from fossil fuels to electricity in our vehicles, homes, and businesses. Now, this is important. If you're in British Columbia right now, this is actually talked about in the phase 2 of the comprehensive review of BC Hydro. This is something that BC Hydro is considering in the future, giving what their end user are requesting of them. So giving you the ability to adopt these rate designs, which would be more beneficial to the environment, but also to utility operations. Now, some of what they've offered up are the ideas for residential customers, which is a time of use rate, which is more expensive during peak times, and then maybe an off-peak time, which is not as expensive. An interruptible rate, where the utility actually has access to your air conditioning or baseboard heating systems, and they can fluctuate the temperature in your home. Also discount rate for heat pumps now, and which is, a good technology for electrifying air conditioning. Now, what I've shown you here is a bunch of arrows, but these arrows show you with each of these rates, there's sort of a human decision variable or a human dimension that's involved, process scheduling choices for the time of use, household satisfaction when you're allowing someone to mess with the temperature in your household, and also technology adoption for the heat pumps. Now, for commercial customers, there's this idea of a discount rate to encourage EV charging, and then also a discount rate to convert district energy systems from natural gas to electricity, which is a fuel switching decision for the bottom, and a technology adoption and human satisfaction on the top. And so the idea is if these optional rates are to permeate through society, sort of what are the range of possibilities and what can happen to the infrastructure, and also with human interaction. So again, some questions are, how will the adoption of optional rate designs influence consumption patterns and green technology adoption? How deep will the optional rates permeate through a service area? How deep do the rates need to permeate to see impactful change from the end users? And you can imagine the question of does this do anything at all? Do these optional rate designs, if they were at full-blown capacity, do they actually result in meaningful change? And again, you can do that without socio-technical modeling, but again, for the ABM perspective, we can see what happens as it permeates through the environment. Now, from another direction that I've mentioned here today is sort of smart city technologies and where that's taking our energy systems. And again, really the heart of smart city technologies is not mentioned here are sensors, which collect the data at different levels of resolution and space as well. So those are really sort of the beginning of it, but maybe some of the bigger players would be blockchain, which blockchain is a platform for peer-to-peer digital transactions and decentralized applications to proceed without the use of a credible third party or intermediary party. So, eliminating some of the efficiency concerns we see with third-party firms and sort of how financial structures work today. There's also the idea of smart contracts, which are a separate technology from blockchain, and they predate blockchain by 10 years or so. These smart contracts are simple scripts that perform automated algorithmic steps using data logged by the blockchain. Now, smart contracts extend the use case of blockchain beyond money, and now they can be used for tailored financial instruments, which we'll talk about here in a sec. And the last piece that connects it all together is the Internet of Things, or IoT, which is a system of internet connected objects that can collect and transfer data without human intervention. Really just a network of devices here. So this next point here is the idea of a token economy. So a token economy is coming whether we want it to or not. And we're going to talk about energy systems in a token economy. Well, cryptographic tokens represent programmable assets. And these can be managed by a smart contract, and their activities can be reported by a blockchain. Now, when you add that third set of technology, which is you're combining the blockchain and Internet of Things, and you combine them, now this can facilitate sharing of services and resources, okay? This can lead to the creation of a marketplace of services between devices. Tokens will act as the medium of exchange in this marketplace. And what this is going to lead to is the automation of existing workflows. Now, what does this all do? This creates novel electricity market structures. And they're designed, or can be designed, to modify human behavior in favor of decarbonization and electrification and sustainable choices and resilience. And there's really a long list of things that they can create structures for. And this is going to lead to, real-time transactive energy market systems. Now, how will the dynamics of power systems evolve under the influence of real-time transactive energy market systems? And how will new alternative market structures impact human behavior and decarbonization efforts and many other efforts? And how effective are they for, frequency and voltage regulation, or really just infrastructure regulation in general? Okay. So again, with this new idea of energy systems in a token economy, there's new applications and new market structures. One of them, as we talked about before, was decentralized energy trading, and a concept of a peer-to-peer blockchain-enabled energy trading platform. And again, these are online platforms where you can facilitate energy exchanges. This integrates smart contract technology and distributed public ledgers, and it allows you to have the immediate settlement of funds for any trade, for any decentralized energy service. The first application of actually peer-to-peer trading happened in Western Australia with a Renew Nexus program. And what this did was huge. From a very small step, it proved that blockchain technology can facilitate real-time markets for decentralized energy services. And the decentralized point is pretty important because it allows either prosumers and consumers or two parties to set their own prices in the market, or at least to adhere to some regulatory structure by which they can do that. So price is a pretty big deal there. So this is, we've modeled it at the residential scale, but there's many more applications from, commercial to commercial interactions, residential to commercial, or even modeling sort of at the scale of wholesale electricity systems and seeing at wholesale supply how they can trade with each other. So there's different scales there. Now, another application of these new novel structures are demand response markets. And I'm really talking about the idea of you can have a decentralized market for demand response market applications. And again, DR, demand response, this is, consumer actions that can change any part of the load profile of utility or region. So DR thus influences the asset dispatch. And therefore, DR market structures influence the utilization of the flexible resource, because the DR market structure will essentially impact human behavior and how they interact with that system, right? And then their choices ultimately lead to the utilization of that resource from an infrastructure perspective. Now, we want to compare and contrast decentralized markets with centralized markets and assess their impact on utilization, curtailment of VRE, frequency regulation, and also greenhouse gas emissions. Another approach would be competing storage markets. There are many studies that focus on, market systems in isolation. It's only an arbitrage storage market, or it's only a frequency regulation market. But what about a system in which storage operators have the option to choose competing markets? And again, sociotechnical modeling can be used to model when there's actual competition between these markets, and how those dynamics and the impact of market choice or market choice can impact utilization and spatial temporal pattern of storage dynamics, curtailment of VRE, frequency regulation, and the like. Now, we're going to take a step back and just talk about major research goals here, and talk about sort of what my research can do, and where we're headed. And the two top points are about sort of the directions we talked about today. We want to determine the system-wide impacts of decarbonization and electrification on electric distribution infrastructure in Canada. We also want to explore the benefits of potential policy reforms in achieving extended electrification and highlight the challenges of distribution system management. We want to evaluate the ability of novel electricity market structures to motivate human behaviors that comply with decarbonization efforts. And, we also want to evaluate the ability of infrastructure investments and operational improvements to alleviate transitional problems that arise from electrification or sustainability efforts. And we also want to assess their economic and environmental outcomes. And the last point is pretty important, is we want to explore the benefits of potential policy reforms, not just for extended electrification, but for clean transportation, for sustainable communities, for renewable energy projects. We want to explore policy for all of these different avenues. And you could imagine probably from your own work how we could apply ABM for this, okay? Now, let's talk about the intellectual merit of this type of research. Well, first off, new methodologies will fill knowledge gaps regarding how household adoption of electric heating and transportation technologies can influence as infrastructure performance, economic and environmental performance as well. We're going to build new understanding on the impact of alternative electricity market structures on human behavior and how human behavior further influences the infrastructure. We're going to bridge social science and engineering disciplines to simulate the impacts of policy movements on human and infrastructure dynamics so that we can study policy movements for smart cities, for energy justice, for resilience. And again, we're going to build new understanding on the impact of policy reform and technological advancement on the feedbacks between investment and distribution and charging infrastructure and increased adoption of EV technology, but also heating technology, new technologies for sustainable futures. Now let's talk about the broader impacts and who this has value for. Well, this research has immediate value for power system management as utilities and balancing authorities design infrastructure for smart grids, and for designing market structures and rates. There's insights are going to be developed about household technology adoption, and the modeling methodology translates directly to decarbonization pathways. You can advise utilities and regulatory bodies as technology adoption gains momentum. Policies can be simulated beforehand using these approaches to assess impacts to human decision-making and infrastructure, but also on the built environment, how they can have an impact on transportation, hydrogen systems, marine energy, really touching on all the points of what we do here at ICEFIC. So again, think about it from your own perspective. And again, the modeling methodologies may be extended to model an entire state or region. And again, we can imagine that states with competitive electricity markets may have very different results, like Alberta and Ontario. And the modeling methodology can be reapplied for many other locations around at varying scales around Canada. All right, so we don't just have to model what's happening in BC, but we can see what's happening on Ontario or Alberta or back east, where use your imagination. Now, to summarize all of what we've talked about today and what we're trying to bring home, what I'm telling you here is that energy networks can be modeled as complex adaptive systems. And agent-based modeling is a computational approach which can be applied to energy systems models to model heterogeneity, adaptive human behaviors, and social communication, really highlighting that human dimension impact. We can model high spatial and temporal resolution. We can model environmental impacts. Again, we're talking about this being a very rich and spatial type of modeling methodology, and inherently can tell us what's happening at many scales across Canada. We can model, modeling the socio-technical dynamics of energy networks can elucidate the challenges of a transitioning system. And I got to really talk about that point. When we look at the evolution of energy systems, which is, inevitable, we always look at it as a point A to point B type of transition. It's not. It's point A to point Z. There's many checkpoints in between, and socio-technical modeling can allow us to unpack and see what happens to infrastructure and human systems as we go through those many, many checkpoints in between. And using socio-technical systems, we can illustrate how human behavior influences those dynamics. Okay, really important. Now, socio-technical, I'm speaking very broadly here, but socio-technical frameworks will provide tools to simulate what-if scenarios for a range of policies and for attitudinal changes, technological advancement, market structures, and climate change perspectives. So, and policies rather. And ladies and gentlemen, thank you so much for your time. Maybe I want to respond to a few comments that I know you'll probably have. One is what is the limitations of agent-based modeling? So for agent-based modeling, some of the limitations are we have a problem validating. Okay, this has been an age-old problem for well over 2 decades. Is ABM can be used to simulate the world, but really, how do you prove that the model assumptions are right? And again, sort of the answer that I have for that is that you need more data collection and you need more efforts to actually prove the test cases that we use for these models. And sort of you also want to make sure that the ABM is modeled at the correct scale, right? Are you really getting the insight out of the right scale that you're looking for? And I just wanted to address that beforehand. But if there's any questions that you have for me, please, let me know now. I'm not really totally restricted by the hour. We got started a little bit later but I'm around. I'm also around after this presentation today. I'll be here for a little while. So if you have any ideas on how ABM or sociotechnical systems can be applied to your own research, let me know. I'm very eager to do work with people in ISPIC and abroad. And again, I'm happy to take your questions now.
Okay, thanks.